Hello, this is Mrs. Nearing. In this video, we are going to talk about the concept of the mole, which in AP Chemistry is topic 1.1, covers both the mole and mole calculations and significant figures. And what is a mole? So one definition of a mole is this cute fuzzy animals that ruins your yard. Um, Another definition of the mole, the way that we will very commonly use it, it's a unit used to count atoms. And the comparison that is often made is with the concept of a dozen. If someone tells you that you have a dozen of something, that word has meaning to it. You know that when you see dozen, we know that it means 12. And it doesn't matter what you are measuring. If you have a dozen eggs, that's 12 eggs. That's this lovely picture right here. If you have a dozen marshmallows, that's 12 marshmallows. If you have a dozen carbon atoms, that would mean 12 carbon atoms. If you have a dozen muffins, that's 12 muffins. So a dozen means 12, no matter what you are counting. The same thing goes for the idea behind moles. The mole is just a much bigger number. 1 mole of eggs would be 6.02 times 10 to the 23rd eggs. That number is really just kind of hard to even imagine how big it is. Thinking about scientific notation, the way you would write this is you take 6.02 and you take this decimal and you move it over 23 spots. You ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 19, 20, 21, 22, 20. I ran out of space. So these are all 0, 0, zeros. This number is just kind of unimaginably large. It's hard to even like comprehend how big this number is, right? It's a very big number. Okay. So again, a mole of marshmallow is that many marshmallows. A mole of carbon atoms would be 6.02 times 10 to the 23rd carbon atoms. If you are wondering, do I need to memorize this number? Well, I mean, you might end up just knowing it because you run into it several times, but this is an example of something that is on your equation sheet. So if you ever needed this number, it would be on your equation sheet that you could refer to. So don't worry about memorizing it. Okay, so try and conceptualize the whole idea of a mole, because again, it's so big, it's kind of hard to even imagine it. So here's some examples for you to just try and picture how big it is. If you had a mole of basketballs, they would fit into a ball bag the size of the planet Earth. So basically 1 mole of basketballs is the same as the size of the Earth, the whole planet. Okay, so there's one example. Another example for you, a mole of marshmallows would cover the entire United States to a depth of 650 miles. That's even hard to comprehend what that would be, 650 miles high. And then a mole of grains of rice, which remember, grains of rice are pretty small, would cover all of the land in the earth to a depth of 75 meters. So a mole, that is a very, very large number, okay? But atoms are super small, and that's why a mole is useful. So if we're talking about atoms or molecules, sorry, I'll scroll this off the side, then a mole is actually a very reasonable amount. If you have a mole of water, that ends up being 18 grams. So if you have 6.02 times 10 to the 23rd water molecules, that ends up being about 1 to 2 tablespoons of water, kind of somewhere in there roughly. Okay, a mole of copper is 63.5 grams. That's around 22 copper pennies. If you got some of the old pennies that are all copper, that's around 22 pennies. So much more reasonable amount. That's because atoms are super tiny. That's why it's useful to have this really large number to use. Okay. And where the mole becomes really useful is this idea of counting by mass, because it wouldn't be reasonable to sit there and count out 6.02 times 10 to the 23rd carbon atoms, and they're too small to see anyways, and how would you do that? And counting all of them would take more time than you have in your life. Okay, so what we do is we use this idea of counting by mass. So this concept of a molar mass, like knowing how much 1 mole of something weighs, allows us to count the number of atoms in a sample by weighing them, and this is just super useful. So for example, I know that 1 mole of carbon weighs 12 grams. So if I weigh out 12 grams of pure carbon, I know how many atoms of carbon are in that sample. So I can basically use mass as a way of counting. So if I want half a mole, I can just weigh out 6 grams. Or if I want 2 moles, I can weigh out twice as much. If I 18 grams of water, that means I have 6.02 times 10 to the 23rd water molecules. So we could, measure out exactly 6.02 times 10 to the 23rd water molecules without actually counting any water molecules. We would just use a balance and find 18 grams of water. So that's super useful. And so there's some checking questions that went along with the reading. This goes along with the reading on page 2 here. And one of the questions is compare the number of atoms in 1 mole of copper and 1 mole of iron. Explain your reasoning. So for this one, and I'm going to go over the answers here. So hopefully you've had a chance to think about this. We'll talk about these. So if you have a 1 mole of something, they have the same number of atoms. So 1 mole of anything has the same number of atoms. So it doesn't matter if it's copper, if it's iron, what it is. So they would have, the number of atoms would be the same in these two samples. That's just kind of the definition of what a mole is. So a mole means 6.02 times 10 to the 23rd of those things. Items. Doesn't matter what those items are. They could be cars, marshmallows, copper atoms, iron atoms, water molecules. Now let's think about it in terms of mass. If I were to compare the mass of 1 mole of aluminum and 1 mole of carbon, what could I say about their masses? Well, you might remember from chemistry looking at the periodic table, and if you look on the periodic table, which you can find in your course resources section of the content library, this value right here on the bottom is what we call the molar mass. And what those numbers tell us, notice how I took a snippet that includes both carbon and aluminum. What this tells us is that 1 mole of carbon weighs 12.01 grams and 1 mole of aluminum weighs 26.98 grams. So they have the same number of atoms, but they have different masses. Okay, so we're kind of just getting some of these key concepts behind the mole. And we'll do one more set of questions here. So these two examples compared what if we had 1 mole of each thing? So we have 1 mole copper, 1 mole iron, 1 mole aluminum, 1 mole carbon. This question says, what if you compare things of equal mass? So what if you have 1 gram of aluminum and 1 gram of carbon? How we compare the number of atoms in them? Well, we know that every 1 mole of aluminum is 26.98 grams. Remember, we saw that on the previous page. And 1 mole of carbon is 12.01 grams. So what this tells us is it looks as though individual atoms of carbon are lighter. So what that means is you are going to need more carbon atoms to get 1 gram than you would for aluminum. It's going to take more carbon atoms to get to reach that 1 gram value than it would for your aluminum atoms. So since each carbon atom is lighter, you're going to need more of them. So your carbon sample would have more atoms in it. We'll go over some mathematical calculations in a moment. The way we could do this mathematically, we'll go over this actually in another video, is you could do this kind of calculation. You could say, well, 1 gram of aluminum, and I know that every 1 mole of aluminum is 26.98 grams. And then if I had 1 gram of carbon, every 1 mole of carbon weighs 12.01 grams. And so this number is 1 divided by 26.98. This is 1 divided by 12.01. So we're going to end up with a larger number here. So your 1 gram of carbon contains more moles, which means it also contains more atoms. So that's another way to answer that question mathematically. Notice I still don't have to use my calculator, right? I don't have to answer this question. I just have to know that 1 over 12 is bigger than 1 over 26. So don't use your calculator if you don't need to. Okay, so our last question here, just kind of think about this conceptually, Determine which sample contains the most atoms. Explain your reasoning or show some mathematical work. But again, I encourage you to do this without doing any calculations on a calculator. So we can kind of follow this model up here. So we have 1 gram of copper, 1 gram of carbon, 10 grams of uranium. And let's look at these molar masses here. So carbon, we've looked at a couple times. I'm just going to write them to 2 sig figs for the sake of this one. 1 mole of carbon is 12 grams. If you look at your periodic table, 1 mole of copper is 63.55. I'm just going to round that to 64 because this isn't a very like sig fig intensive question. And then here, uranium, that is the element U. Okay, uranium over here, 238. Okay. 238. So which one contains the most atoms? So there's some different ways you can think about this one. What I might do is I'm going to set it up mathematically, kind of like this example up here at the top. So if I had 1 gram of copper, and I know that 1 mole of copper weighs 64 grams, that means I have 1 over 64 moles. 1 gram of carbon would look like this. I've got 1 over the 12 moles, and then this would be if I had 10 grams of uranium. So I've got more uranium, but it's also heavier. So that's 10 divided by 238. Whoops, 238, which is about 1 over, I can round that to 1 over 23.8. It still looks like the one that's kind of the biggest number is going to be your carbon. Okay, so your 1 gram of carbon is going to have the most atoms in it. It is the lightest, so you're going to need more of it. Yeah, so those are some kind of conceptual questions. I know I got into some math here. You didn't necessarily need to do the math route on these problems. And if this math part makes you uncomfortable, I'm going to put out another video that goes over some mole calculations as well. So you can also go over that. All right. Thank you for listening.